Seems like I touched a nerve with these videos. In the previous one about Cedar Pattern, I made a few statements that annoyed some people who subsequently felt compelled to comment and inform me that the electric universe is a far better theory than the established theory. Which is weird because last time I checked, the electric universe hadn't produced a single testable hypothesis. Apparently, I should read up on the great minds like Velikovsky, which I did, and it was funny as fuck. You should do the same. Apparently, the Sapphire project also clearly proves the established theory wrong. Now, don't get me started on that clusterfuck of incompetence. Actually, I may do a thing on that. Well, I won't lie, I have had a few good chats with people as well, so I do have to recognize that. But the response was pretty funny, considering that the video wasn't really about the electric universe. I was merely commenting on a presentation from Cedar Pattern where the creator dedicates a whole video to actually set the context for this structured atomic model idea. I just explored his claims that the established theory cannot explain things like the patterns in the periodic table, which the theory explains really well, or his other claims that the accepted theory doesn't explain why atoms emit alpha particles during radioactive decay and not protons, deuterium or tritium, which is really easy to explain, as in high school level easy. But anyway, let's dive into the third, and as it stands, the final video on his series about the atom, where we will be exploring this fabled structured atomic model as developed by Edo Kaal.
The structured atomic model was created by Edo Kaal 12 years ago.
And already shown to be incorrect 52 years ago. Interesting how that works. Looks like Edwin, or Edo, wasn't aware of a few things when he developed the model, and this should raise a red flag. There are many cranks who claim that they have a framework that addresses all the shortcomings of the established theory, but they almost always demonstrate that they haven't understood the theory. How can you show a theory to be incorrect if you don't understand it, let alone develop an alternative? At best, what you can hope for is that your framework is better than some straw man version of the theory. But we will let our host explain the basics.
And there is now a team of people who work on this from many different aspects, continually refining and seeking answers. Unhappy with the conventional model, and with the many mysteries that this throws up, he set himself the challenge of rewriting the book on the atomic structure. The basic premise of SAM is beautifully simple. There is no such thing as the neutron. The neutron is redefined instead as a proton and an electron. Two protons can be held inside of the nucleus using this electron.
Now I could just stop here. This is quite simply and demonstrably untrue. For this we look at the deep inelastic scattering experiments performed in the late 60s all the way through to today, where we fire electrons at nuclei. When firing them at baryons like protons and neutrons, there are 3 deflection points corresponding to the 3 quarks that these baryons are made up of. Okay. There's no issue here. Actually, it doesn't even require you to accept the existence of quarks. All you need to accept is that there's an experimental result that shows that there are 3 points of deflection for protons. If a neutron were actually a proton with an electron, then we would see a different result. We would expect the 3 deflection points from the proton plus a 4th deflection point from that electron. And we do not observe this. So, that's it. This idea is dead on the whiteboard. Goodbye. Of course, there are other problems which we will touch on a bit later, as they present some interesting topics.
This means that the force holding these particles inside the atom is not the mysterious strong force, but instead this concept postulates the use of the electromagnetic force.
But here's another problem. The strong force exists and you can't just dismiss it. The issue is that the strong force doesn't just hold protons and neutrons together, it also holds quarks together to make a nucleon. And actually that's the main thing that the strong force does. However, the force holding the quarks together is huge, but almost completely cancelled out. Note the word almost. It isn't completely cancelled out. The result is the residual strong force, and this is the bit that actually holds the nucleons together. But the bottom line is that you cannot discard the strong force and expect protons and neutrons to still exist.
The charge of this nucleus is still +1, but it contains the mass of 2 protons and an electron. And this is why we think the neutron has no charge and has a mass which is slightly heavier than a proton.
Ah yes, let's run the numbers. The mass of an electron is 511 keV per speed of light squared. The mass of a proton is 938.272 MeV per speed of light squared. The mass of a neutron is 939.565 MeV per speed of light squared. Add electron mass to proton mass and then subtract the neutron mass to get that the neutron mass is still 782 keV per speed of light squared larger. So that doesn't add up. But of course, it's not that simple. It really isn't, but that's not going to help your case. What the theory describes is a proton which comprises 2 up quarks and 1 down quark. A neutron has 2 down quarks and 1 up quark. Now, the down quark interacts more strongly with the Higgs field, which is just a fancy way of saying that it has more mass. The neutron has 2 of these particles compared to the proton, which only has 1. Interestingly, when you add up the rest masses of the quarks, you actually still come nowhere near the mass of a proton, only about 1%. And this has to do with quantum chromodynamics and the uncertainty principle, which we will touch on in a bit.
As this force acts across all particles, it will cause the nucleus to settle so that the particles are spaced as tightly together as possible. This is referred to as the densest packing geometry. This will create compact spherical shapes which form the building blocks from which the larger nucleus structures are built. Each of these components will form the densest packing shape, but the entire nucleus will not, as this is created by combining these shapes together. The most stable shapes are the tetrahedron, the icosahedron, and the pentagonal bipyramid. Each element in the periodic table is made of these shapes joined together in a semi-static state. Let's examine some of these basic blocks to understand how an atom can be constructed in this model. When we examine the periodic table, you will notice that most of the time you need to add 1 proton and 1 neutron to get to the next element. There are, however, some exceptions to this, and the conventional model cannot explain why this is the case.
Once again, he claims that the established theory cannot explain something when it does, and in very simple terms as well. I think that there should be a special name for this kind of straw man. Let me know in the comments section if you can think of one. The bottom line is that you are welcome to challenge the theory. You can disagree with it, and that's absolutely fine. You just need to demonstrate that it is incorrect, and then there will be a scramble to change the theory. That is how it works. However, you do not get to claim that the theory doesn't provide an explanation when it clearly does, and use that to plug in some nonsense. Protons and neutrons are both fermions, which means that each proton or neutron energy level can be occupied by 1 spin up and 1 spin down version of the respective particle. As you add protons or neutrons to the nucleus, the particles will fill the next lowest available energy state. But in simple terms, the difference in energy between each subsequent state decreases as you go up. However, this difference decreases more rapidly for neutrons due to their lack of charge. So as a result, there are more states available for neutrons over a given energy range than there are for protons. Interestingly, this is also involved in beta minus decay. A neutron may be in an energy state where there is a lower energy proton state available, and in due course a neutron may emit an electron and an electron antineutrino, so it can become a proton and occupy that lower energy state. This is the universe just being lazy.
In the following sequence, you will see that I show how many particles need to be added in both the conventional and the SAM model to get to the next element. We start by looking at deuterium. In the conventional model, this is made of a proton and a neutron. Here we have 2 protons joined together by an electron. If we examine this structure, you will see that there are 2 areas of positive charge, and this allows the outer electrons to have 2 poles to be attracted to. The electron at the center is either toroidal shaped or has a particle which rotates around the touching points or is smeared out. Helium-4 has 2 protons and 2 neutrons, and in this case, in the SAM model, we have 2 deuteriums connected across the central electron, forming a tetrahedron shape. As we now move across the periodic table, you will start to see a pattern appearing. Starting with lithium, we again add a deuterium. Here we see the atoms arrange themselves into the densest packing shape, and in this case, this is a pentagonal bipyramid. And this leaves several open spaces where we could once again add a deuterium to move to the next element, beryllium. From beryllium, we continue to add deuterium to the same face we were adding to before, and this makes boron. As we continue adding deuterium in each step, the protons will rearrange themselves into the densest packing shape. Slowly, the gap in the middle grows until we reach carbon. Here, each proton now touches 5 other protons, and the shape is perfectly symmetrical. It is an icosahedron.
Okay, is anyone else spotting the problem here? First, let's take this deuterium nucleus where we supposedly have 2 protons with an electron in the middle. The charge distribution is such that one could imagine that this whole thing would stick together if we ignore the other problems. But let's take the carbon nucleus, which supposedly has 12 protons and 6 electrons. On the image here, we have the electrons sitting between these 2 protons, so their charges are shielded. But then you have these protons where there is nothing shielding their charges. So the problem becomes that you need to stick an electron between each proton because remember, there is no strong force in this model. And this means that you have to add 30 electrons to ensure that each proton is shielded. But this means that your nucleus ends up with a charge of -18. A better way of setting this up would be if you just had all the electrons buzzing around in the core and the protons are arranged in a shell around the outside. But the repulsive force of the protons would still be really large, and unless you have sufficient electrons inside so it can glue the shell together, the whole thing would just fly apart. But this doesn't address another massive problem which this model has. Let's go back to the deuterium. What this suggests is that there's an electron confined between these protons, and there's a problem here. Electrons do not like to be confined. From the uncertainty principle, we can calculate the minimum kinetic energy of an electron confined in a box with each side having a length L. Now let's be generous and say that the electron is confined in a square box with a length equal to 2 femtometers. We get the kinetic energy of that electron at 85.72 giga-electron volts, and this is insane. This energy has a mass equivalent of just over 91 protons. Now, I will admit that nuclear physics is not really my forte, but this seems rather silly to me. Oh, and remember my comment about quarks? Well, they are fermions as well, and the uncertainty principle holds for these, and a large part of a nucleon's mass actually comes from this kinetic energy by virtue of these particles being confined.
Carbon represents the most basic structure of the nucleus. It is the most densely packed and has the strongest binding energy.
Details again. Here is your graph for binding energy per nucleon, and this is where carbon sits.
And is the basic building block upon which the next elements are built, as well as the building block for life itself. From here we can add deuterium to any of the sides, and in doing so will bring us to nitrogen. Continuing to add onto the same face with nitrogen, we move to oxygen. From oxygen, we need to add 1 proton and 2 neutrons in the old model to move to the next element. But in our case, we would add 1 deuterium and 1 proton-electron pair. The structure will determine, to a large extent, where the protons can be located. You will notice on the oxygen structure that there is a gap growing here, and this will restrict a proton from wanting to settle there. If we examine fluorine, we see that one of the protons will occupy the spot near the previously added deuterium, and the others will have to start at a different location. These simple rules mean that finding the location and the shape of the nucleus is almost self-deterministic. Now we just add 1 additional proton and we jump to neon. This now creates a shape that is symmetrical across the center. From here, in order to jump back to the start of the table, we need to add 1 proton and 2 neutrons. So in our case, we would be adding 1 proton-electron pair and 1 deuterium. And we now have sodium. And if we compare the shape, we will see that it is the same ending on one side as lithium, which sits above it. Moving along to magnesium, you will now see 2 active areas which are essentially 2 lithiums. As we continue to move across, you will see that aluminium has striking similarities to boron, which is above it. When we jump to silicon, we once more see that at this point, the end to which we were adding protons has become full, and looks like a carbon on one end. So this pattern continues across the periods. Each time we add a proton or an electron-proton pair, there are only a certain number of possible locations it can go in. As you build, you are adding to a tetrahedron shape, and this determines valid places that they can be added. This means that there are certain shapes that are not stable. You will notice that sometimes the number of particles added is not always consistent in the periodic table. This is a mystery in the conventional model.
No, it's not. I've already explained why this is. In addition, there's absolutely no reason why this model would explain it either.
But using SAM, we can understand why some of these atoms are not possible or are not stable. It is because of the fact that some of these intermediate structures are not stable.
So, the structures are not stable because the structures are not stable. Got it.
And this is due to the geometry, and this is something that we will explore in more detail in a future video. As we continue to add to the nucleus, it creates nodes from which further protons can be added. Initially, this is at either end, but as the structure grows, branches will start to appear on the sides and ends.
Okay, so who's spotting another problem here? It is pretty well established that nuclei are not spherically symmetric. This is indicated by something called the electric quadrupole moment and quantified by something called the Q value. If the value is non-zero, then the nucleus is not spherically symmetric. The charge distribution becomes more prolate for positive values and oblate for negative values. But here's the problem. If we take, say, cesium-133, for example, which is pretty close to being spherically symmetric with a Q value of minus 0.003, and we look at what the website shows its structure to be, then we find that it's not listed. But we can look at the nucleus before that, and we go for xenon-128 to get cesium-133. We just need to add a proton and 4 neutrons, or 5 protons and 4 electrons, whatever. Now, can you find a location where you can do that to result in a shape that is even close to being spherically symmetric?
As these branches grow and the nucleus gets larger, these branches can start to interfere with each other. The branches will determine what products are created in nuclear reactions. No more will it be random, but now it depends on where an incoming neutron strikes, as to how a branch breaks. We will explore this in much greater detail separately. The shape of the nucleus and the fact that we see similar shapes within the groups is the reason why they have similar properties. If you wish to explore these patterns in more detail, you can explore the SAM periodic table as well as the atomic builder at the etherealmatters.org website. I will put the link down in the description. There are many aspects that this model could help explain, from magnetic moments to the boiling and melting points, and at the same time, it makes us question some fundamental assumptions about what electrons are and whether they really orbit the nucleus and what exactly a proton is. This model makes no presumptions on any of these and can comfortably work with either a solid particle or not. So let's jump back to the structure of the atom and ask some initial questions which will hopefully set your mind in the direction that we'll be heading for in the future. In order to hold the protons in the nucleus, this model employs the electromagnetic force. The electron acts as a glue binding the protons in the nucleus. The question then becomes, if it can do this, what does it look like? Examining some of the more complex atoms reveals that in some cases it is better to consider the electron as smeared out particles which exceed the size of the proton. It acts like a glue which is able to extend outwards.
Okay, so that addresses the problem of the number of electrons. And it lessens the problem with the confinement of the electron energy a bit, although not by much. And oh boy, there's a whole host of problems that this introduces.
Nuclear decay reactions show us that when a neutron is ejected, it quickly decays into a proton and an electron and an antineutrino. In this model, we see that this came from the proton and the electron pair in the nucleus. So does the electron change shape once it becomes decoupled from the proton? Why is this pairing not stable outside the nucleus? And what on earth is the neutrino? And what was its equivalent in the nucleus?
Okay, and we circle back to that issue. And this is the thing that actually originally had me going because, well, I'm a magnetism nerd. Protons are spin 1/2 particles. Electrons are spin 1/2 particles. So if we add an electron to a proton, we have two options. Either their spins are aligned and a neutron then has a spin of 1, or they're anti-aligned and a neutron has a 0 spin. Of course, we know that neutrons are spin 1/2, so there has to be that little neutrino in there to make it all work, as angular momentum is a conserved quantity. Interestingly enough, the reverse is kind of the thing that led to Pauli hypothesizing that the neutrino exists. The observation of a neutron decaying into a proton and electron appeared to violate the conservation of angular momentum, and he hypothesizes that there must be this other spin 1/2 particles with no charge that gets emitted. But anyway, the question that the structured atomic model would indeed need to answer is, where is this neutrino before decay? Because spin has to be conserved, and the standard model has 12 spin 1/2 particles and their corresponding antiparticles. Now, the charged particles are a big no-no, which only leaves the neutrinos. The muon neutrino and the tau neutrino are too massive, so that really just leaves the electron neutrino or the electron antineutrino, which is fine as the latter is what is emitted during decay, but neutrinos do not carry charge, so they don't interact via Coulomb forces. They don't interact via the strong force either. The weak interaction doesn't have sufficient range, and gravity is sure as hell not keeping it there. So what keeps the neutrino there? Or indeed, what is it before the emission? We've already established that it's not going to be one of the other fermions, or are you suggesting a whole new class of subatomic particles? In which case, I'm interested. The next question, that's probably a bit simpler, is also around beta decay. So let's take the neutron as being a proton with an electron and an antineutrino. Fine. But what about beta plus decay? Because this is where a proton changes to a neutron and emits a positron and an electron neutrino. So is the proton a combination of a neutron, positron, and an electron neutrino? But then the neutron inside that proton is a combination of a proton, electron, and electron antineutrino. Basically, is it just turtles all the way down?
At this point, it is important to note that this is work in progress, and although Edo and the SAM team have made great progress, there are still many unanswered questions. Some of these questions we will also be exploring together with Edo and the team. In the coming episodes, we will examine the evidence that underpins this model from both nuclear reactions and SAFAR, as well as explore alternative ideas for the electron and the proton, and the structure mechanics of the SAM model itself. As always, be brave, be curious, the truth is waiting for us. Until next time.
On the surface, the whole structured atomic model looks interesting. It is simple and the little diagrams are aesthetically pleasing, but there are a whole host of problems there that are just too big to ignore. I would get it if it were a hypothesis in its early days and there are some problems with the finer detail. After all, Rome wasn't built in a day. The problem with this whole thing is that even though the core idea is quite nice and rather simple, it would be lovely if it were correct, the problem is that it is just wrong, and the basic fundamental assumptions of the model were already shown to be incorrect years before it was developed. At the end of the second video in this series, I inserted this clip from Richard Feynman.
First we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is, it doesn't make a difference how smart you are who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Well, we have taken the guess and figured out the consequences. We compared that to observations, and we can conclude that the guess is wrong. So I think that I will leave it at that. A massive thank you to my patrons. You rock, you know who you are. And of course, thank you all for watching, and until next time.